If you go into the 30th minute, I will politely step in and open the floor for questions. Cosmo, do you have any questions for us before you get started?
I don't have a question, but I have a little thing to say.
Yes,
I
ma'am.
mean, we can speak English quite good, but we could maybe recommend to you to activate the live undertitle section. But you also have our script, so you can refer to what we're saying. Just a little hint, maybe it helps.
That's all right. I'm using my high school German to kind of, know what you guys are saying. So I catch every once in a while. I catch 2 or 3 words. It's been a while since I've been in high school.
Guten
So,
Tag, schön dich zu sehen.
ich heiße Catherine. Wie heißen du bitte?
Wow, ich heiße Cosma. Dankeschön.
Hi. Like I said, that was before you were born. It was a long time ago.
Yeah.
All right. So, I think I already said this, but I'm going to say it again. You have 30 minutes for your presentation, and you may start when you're ready.
All right. So, good morning, dear Catherine, dear Christopher, and Zach. Hello, Herc Implementation Team, and thank you for this opportunity to present our work. We are the Robonauts from the Jesco from Puttkamwer School in the Highscvhool division, participating at the NASA Human Exploration Roverchallenge 2025 with a human-powered rover. I'm Cosma Heckel, I'm 17 years, and I'm doing a dual apprenticeship for becoming an industrial mechanic next to my A-level. I am the team leader, coordinating the team next to being active in every working field, and I'm going to be the pilot of this year. I am depicted in the middle of the photo.
Hello, my name is Maura Buta. I'm 18 years old and currently doing my A-level. I'm working on my pilot license to attend the training of a fighter pilot. I support the team with technical designs and organizational tasks. You can see me in the picture at the left.
And I am Leander Dürert. I'm 15 years old and very interested into space. I love 3D printing and construction precisely. I'm the safety officer and responsible for ensuring our systems are secure and reliable. In the picture, I am located on the right side. Okay, let's dive into the journey of designing and building our rover Ophelia.
Slide 2. Fail, try again, and fail better. Our analysis. Our rover's design prioritizes adaptability and performance. The first major challenge was the length of our rover. As shown in this figure, the original configuration limited leg room for the co-pilot, reducing their pedaling efficiency. To address this, we introduced an adjustable extender, as illustrated here. This solution allows the rear axle to be customized to the co-pilot's height, ensuring both comfort and maximum power transmission. This adjustment process is straightforward, requiring minimal time and tools. We also improved the seat mounts. Previously, the rear seat mount broke during 2024 race due to a cold weld, compromising safety. This figure shows the redesigned rear seat mount milled from a single piece of aluminium, which enhances both durability and safety.
Slide 3. Turn around the comfort zone. In 2024, our co-pilot experienced significant discomfort due to the lack of rear suspension, as shown in those figures. This problem stemmed from vibrations and uneven terrain, which the front suspension absorbs, but the rear did not. Our solution is a fiberglass spring integrated into the rear axle, as depicted here. This spring absorbs shocks effectively, ensuring a smoother ride for the co-pilot. The spring thickness and flexibility were chosen based on material testing and performance analysis.
This rear suspension not only improves comfort, but also protects the structural integrity of the seat and axle, reducing the risk of damage during races. Slide 4. Wheels are our shoes. Our wheels faced several challenges in 2024. This figure illustrates the damage threat from the last year's race, highlighting its narrow width and vulnerability to tearing under stress. Our solution was to increase the thread width to 15 millimeters and the thickness to 10 millimeters. Additionally, small rubber stoppers are going to be attached using mounting screws, providing extra grip on uneven terrain. These stoppers improve stability on both flat and rough surfaces. To counteract brittleness caused by UV exposure, we reinforced the rubber material with protective materials, extending the thread's lifespan. Each design modification is about to be tested and extensively under simulated race conditions.
Slide 5. Segment by water spout. Our wheels are a core component of the rover's performance. This figure shows the wheel design, which includes 2 laser-cut aluminum discs, a central hub with irregular bearing, and a rubber thread cut precisely with a water jet. The framework consists of 19 plastic tube segments supported by screws and aluminum tubes. This modular design, visible in this figure, ensures flexibility and durability. Each segment absorbs vibration, enhancing stability while protecting the wheel structure. The addition of a second inner tube segment ring acts as a limiter, preventing excessive deformation during use. These modifications ensure the wheels perform reliably across diverse terrains.
Slide 6. The drivetrain. Our drivetrain is designed for efficiency and precision. This figure illustrates the differential gearbox, which enables the wheels to rotate at different speeds during turns, ensuring stability and maneuverability. We have 4 bicycle chains in our rover. The first chain is connected to the sprocket of the pilot's pedals and to the roll-off transmission. The second chain connects the roll-off transmission and the differential transmission at the heart of the front axle. Between chain 1 and 2, the speed transmission takes place in 14 gears through the roll-off transmission. Chain 3 connects the differential gearbox and the roll-off gearbox of the co-pilot. Between chain 2 and 3, the differential gearbox transmits power via universal joints to the shafts and finally to the wheels. The differential gear also translates the speeds of 2 front wheels when cornering, as I said before. Chain 4 connects the co-pilot's roll-off gearbox to the co-pilot's pedal sprocket. Between chain 3 and 4, the speed ratio takes place again in 14 gears through the roll-off transmission.
The roll-off speed hub, shown here, offers 14 evenly spaced gear ratios, providing flexibility for steep climbs and high-speed sections. Each pilot can adjust their cadence independently, optimizing power output.
Slide 7. Steering, suspension, and brake. Safety is integral to our design. This figure highlights our hydraulic braking system, featuring oversized discs for maximum stopping power. The steering brake, also visible, stabilizes the rover during jumps and rough terrain. This figure illustrates the steering geometry, which ensures both wheels align correctly during turns. The steering arms, marked in the red ellipse, connect the wheel bearings to the tie rod, marked in the blue box, enabling easy steering with minimal force. They also secure the brake levers for both the brake and steering brake system. This precision reduces strain on the wheels and enhances overall control. These systems underwent extensive testing to guarantee reliability under race conditions.
Slide 8. Not for everybody. Our carrying unit integrates functionality and durability. This figure shows the ultralight aluminum seats developed with Haas bikes. These seats, which are foldable and interchangeable, optimize both comfort and efficiency. The base frame depicted in this figure incorporates a torsion joint that allows the rover to adapt to uneven terrain. This flexibility ensures all wheels maintain contact with the ground, enhancing stability during off-road navigation.
Slide 9. Check. Compliance with PERC requirements was a key focus. The shown table summarized the rover's dimensions, ensuring it fits within the 5 by 5 by 5 feet cube. Table 3 outlines the weight distribution, which remains within allowable limits.
Compliance with HERC requirements was key focus. The shown table summarized the rover's dimensions, ensuring it fits within the 5 to 5 to 5 feet cube. Another table outlines the weight distribution, which remains within allowable limits. In driving mode, the rover measures 1.36 meters wide, 2.86 meters long, and 0.96 meters high. When collapsed, it remains its width at 1.36 meters, but compressed to 1.03 meters in length and 1.5 meters in height. This compact configuration ensures the rover is portable and meets the competition's size constraints. Regarding weight, the front axle is the heaviest component at 31 kilograms, constructed from aluminum, steel, PLA, and fiberglass. The back axle weighs 8 kilograms, combining aluminum, steel, and plastic. Each seat weighs about 3 kilograms, made of lightweight aluminum and plastic, ensuring the pilot's comfort without compromising structural integrity. Lastly, the wheels weighed 5 kilograms each, designed from a combination of aluminum, steel, and reinforced plastic. These materials were chosen for their balance of strength and weight, which is crucial for maintaining the rover's stability on rough terrain. These specifications reflect our careful consideration of the competition's requirements. By balancing size and weight, we ensure the rover's maneuverability and endurance, especially on challenging obstacles.
Slide 10. Project Plan. 6.3.1. The rover is capable of operating on inclinations of up to 30 degrees. 6.3.2. It has a turning radius of slightly less than 3 meters or 10 feet. 6.3.3. The rover has an exact height of 1.35 meters, which is
smaller.
That is 6.3.5. It is equipped with self-made non-pneumatic tires. 6.3.6. The rover does not use a battery or an electric motor. Its only propulsion comes from the two individuals who drive and control it.
Slide 11. Project timeline. Our project timeline outlines all the key steps we've taken to prepare for the NASA Roverchallenge. It ensures that every aspect of our project, technical development, team coordination, and outreach stay on track. The timeline uses color coding for organizing the tasks. Blue represents the rover development, including design, testing, and assembly. Green covers organizational tasks like team meetings and logistic planning. Yellow marks documentation deadlines, such as the design review report and more technical requirements submissions. Orange focuses on outreach activities like fundraising and our STEM workshops. Our key milestones are, for example, this presentation right now, but also on the 7th of February, the submission of the technical requirement form confirming our rover meets all the NASA specifications, or also on the 27th of February, completion of final presentation materials. And of course, the holy thing from the 10th to the 12th April, the race. Adhering to our timeline was critical. This table outlines our adjusted schedule, which accounts for the early transport of the fully assembled rover to the USA. This proactive planning ensures we have ample time for final adjustments and testing before the competition.
But until now, we have successfully met every deadline, completing all tasks on time without delays. This reflects our team's dedication and efficient planning.
Slide 12. Budget plan. Participating in the NASA Human Exploration Roverchallenge requires careful planning, not just for the rover, but also for our team's logistics. This table breaks down the estimated travel costs. Explanation. Flights for a team of 10 costs €800 per person, totaling €5,600 for the whole team. This includes round-trip tickets from Leipzig to the United States. Additionally, transporting on site, such as car rentals and fuel, costs €19 per person for fuel, totaling €133. Catering is another essential expense, estimated at €150 per person, adding up to €1,050 for the whole team. These costs are necessary to ensure our team members are well prepared and comfortable during the competition. Linked to the project plan. These expenses are part of our larger budget plan, supported by our sponsors and fundraising efforts, ensuring we have the resources to represent our school at this international event.
Our team relies heavily on the support of sponsors and donors to make our project a success. The table on the right outlines the contributions from various partners who have provided parts, tools, and financial support. To keep it short, we are supported by following sponsors: Medler, Hase Bikes, Holm Metall, OAT Street Building, CNC Turnery Günther Jakob, Bosch Car Service, CNC Eichmann, Saddlery Kübler, Chamber of Craft Leipzig, Egos GmbH, First Mold GmbH, and the Space Hotel. We have already received €11,000 from these sponsors, and we are expecting an additional 5,600 in contributions. Their support is really essential to ensuring the success of our project and our participating in the competition.
Slide 13. STEM engagement and budget. Our STEM engagement as Artemis 1 launch witnesses allowed us to share experiences with our community through country tours and presentations.
As STEM engagement, we produced and sold autograph cards with VIPs, earning €200 to €350 per event, plus additional fees for presentation.
These efforts have helped us manage our budget effectively, ensuring all project needs are covered while inspiring our community about space exploration.
Our rover was also exhibited for over a month in a DLR school lab in Cologne, where hundreds of young, interested people learned about the history of the rover and the NASA Human Exploration Roverchallenge. But we will tell you more about this in our STEM engagement review report. Through these activities, we've connected with the public, raised funds, and built excitement for our mission, ensuring strong support for our journey to the NASA competition. Also, our rover. Slide 14. Travel. And finally, for closing our presentation, we would like to show you our latest TV interview. Is that okay for you?
Yes, you can show.
Sure. Sometimes
Great, let's
video
go.
doesn't play very well through Teams, but we'll try.
I might have picked a slightly unsuitable outfit for a business event like
Oh, we
Formnext
can't hear the
2024.
sound. Do you hear the sound?
No, there's no audio.
I might just find
Okay.
somewhere where it's
Ralph,
exactly
can you
right.
check this?
Follow me.
There's no sound.
Okay, so we have sound.
Yes.
Wow. Hi, I'm Sylv. What's this?
Hey, I'm Cosma. This is a moon rover. Students like me build it to take part in a challenge called NASA Roverchallenge in the US.
I'm impressed. Can I jump in?
Yes, of
Take a
course.
ride?
Take a seat and let's go.
Wonder how fast this goes. I'm a bit scared. Whew.
We'll be surprised.
Hold on tight. Ah! Cosma, does it have a horn?
Of course.
This is fun. It's great. Woo! Do you need a license to drive it?
No, on the streets you don't need any license, but you should be sure that you are able to drive this vehicle.
This one was pretty hard. You know, it's good leg work.
Oh, how was it?
It was a hell of a ride. That's great. Thanks. Oh, wow. Thank you so much. That was fun.
I'm happy you
Loved
liked it.
Loved it. Great. Are any of these parts 3D printed?
We now mainly use it for prototyping, but let's see what the future brings.
Let's see what the future brings. Who knows? In the future, there might be entire carts printed in 3D, except for the wheels, of course.
Yes, so this was our latest TV interview. It happened actually just 2 weeks ago at the Formnext fair in Frankfurt. It's an international fair for additive creating, like 3D printing. It was great to see so many new innovations and also great to represent our team. So thank you very much for your attention. We hope that you liked it and we're open for questions.
All right, thank you so much for your presentation. Please leave these slides up in case they want to reference a slide when asking questions. And yes, that was a fun, looked like a fun interview that you had going there, and congratulations on that. Chris, do you have any questions for the team, sir?
Sure. So I have a question about the gearbox. How do you actually change the speeds on that?
Of course, I would answer this question. We change the gears through through the, how can I say, like adjustable Bautenzug. It's it's a little steel wire that goes to the gearbox, and that's how you can switch the gears. The switch is located at the handlebar where you grab and steer the rover. We haven't depicted it yet, but we have to build it. So you're going to hear more about it in the ORR.
Okay, so you have a brake on one side and then the gear shift on the other side?
Yes. Almost correct. We got on the right, we plan to put on the right handlebar the brake for the wheels and also the switch for the gears. Because most of our drivers, also me, use the right hand more than the left hand. So that's why we can manage gears and the brake more efficient. And on the left bar, there's going to be the brake for the steering when we drive over obstacles.
Okay. All right, and then you talked about adding some chain covers at the hinge point. Can you describe that a little bit?
What do you mean? I couldn't understand what you mean.
For safety at the point where it hinges, I think you said you're adding some covers to the chain there.
Oh, yes. Yes, I hurt myself last year or this April with it. We're planning to put 2 discs on the side of the sprocket so that no finger or anything can come between and will be hurt.
Okay, so you're not going to route the chains anywhere. You're just going to put it like a shield in front of it.
Well, we planned, to do this because the chain wasn't a problem. It was the sprocket that had holes where you could put something through, and then
Gotcha.
So the chain wasn't a problem. It was the sprocket, and yet we think it's not a big problem for the chains, because when we collapse our rover, the chains are also bent, and if we would put like a pipe over the chain to secure, we could not really collapse. We would not be able to collapse our rover fully.
Yep, great answer. That's all I have. Thank you. Zach?
Alrighty, thanks, Chris. So, can we go? I think you updated your presentation some, so and that's fine. But I'm going to reference slide numbers, and if they don't match up, I'll just try and get you to the one I want. It was originally slide 5, which
Which one was it?
It's the one with the wheel, the rendering of a wheel, not the picture of an actual one, but it's like a CAD model.
This one, right?
Yeah. So that's
slide 5, yes.
Yeah, slide 5. Yeah. The spokes and that. The spokes and the rim here. How is that being fabricated?
So the aluminium discs at the side are going to be lasered from our sponsor Hol Metal. They have laser machines, so they can laser it out of, I think it was 1 millimeter aluminium plates. And then to assemble, you see the little fingers at the outside of this disc, maybe on segments. We will have to bend them with like our hands, or with the pliers, with some combi pliers, so that they have the right angle, so that the plastic segment can fit in. And then we're going to inject the screws into the pipe, so it will be fixed on the wheel.
Okay, and the two different aluminum segments, you said those are only about 1 millimeter thick. You said.
Let me check. I think it was 2 millimeters. 2 millimeters.
Okay.
Sorry.
And how are they? I mean, it looks like there's rods or something between them, but how are they held together then around the hub?
That's a very good question. At first, they are held together through the middle, where the axis is sticking through. Because also it's like on a bicycle, there in the middle you see there's this kind of pipe. So it is fixed on this. And on every, like, you see the cross interfering, like on the inner circle with the outer. On these places there are screws. Like at first there are little aluminium pipes that are holding them in a separate distance between the discs, and to press them together, we put a screw through and secure them on the other side.
Okay. All right, and I noticed it mentions there that there's one of the bullet points says is a strength test. I guess, how is that strength test done, or what is the method by which you perform the strength test? Because, and the reason I'm asking, or concerned, I guess, about it is that 1 to 2 millimeters is fairly thin, and aluminum is a good material for constructing these sorts of things out of, but it does tend to fail pretty catastrophically when it goes, right? And these aren't particularly thick spokes, so I just want to know to what degree will you be testing it, so that you're confident you're not going to have like a rupture or one of the spokes collapse.
That's another good question. So before we used how's it called, steel, like the steel that won't oxidate. We used it before stainless, because we think it's stainless steel, because it's going to be more strong. But it worked perfectly, and we wanted to reduce our weight. So that's why we switched to aluminum discs, and we tested them with just building them and then making very safely a test drive. And then when we saw, okay, they were working quite good, we were testing on more rough terrain. And since now, nothing broke, nothing bent. So that was our test. We did quite big stress test, and nothing was broken. So that's why we think
Okay.
good.
So so that's a very performance, or I guess application-based testing, but there was nothing like a load cell or a measurement device of any sort that you were using. It was just take it out and rough it up, if you will, but and assume that that's sufficient.
I mean, we personally think you can or we cannot really test this wheel without really driving on it, because the challenge this wheel has to face is the race, and I think no external tests will give the condition, give the how can I say, give the combination of stones and fields and load and trust than actually testing it. So that's why I think our most important testing method is to actually try to drive with it and to test if it's able to work. Because, you know, if we do some tests that cannot really describe if the things will work, then we can fail on the course, and that's not what we want.
Right. No, and I don't disagree that sort of performance evaluation is incredibly useful. The only, I would say, the only sort of downside to it is that you never really know how close to failure you got. Right. If you don't have a measuring device and test something to the point where it either breaks or you're well in excess of, you know, realistic performance, you know, conditions, right? You could say, you know, we tested it to, you know, so many thousand pounds or newtons or whatever, and on the course it would never even get half that much. So we know we have a factor beyond 2, right, of safety there. You never really know for certain how close, like I say, how close you might have gotten to the actual threshold without a measured test. But you're right. As long as you never ask more of it than you did during your evaluation, you're sort of then you likely would have no failure. No argument there.
Actually, Zach, your explanation is really interesting, because really good. We have also thought about it, and that's why we not only have made 2mm big discs, we also made a thinner. Sorry, I forgot to tell you that, but also thicker material, about 3 to 4, but also smaller, like 1.5mm, and also 1. So the 1 failed. It was bending, you know, when we were driving curves, the force was forcing us into the curve, so it bent, like the whole disc was bending a bit outside. So that was our knowledge, okay, that's not enough thickness. So we got some testing. We did not measure it because we also think that if something at the wheels break, then it would be the segments, because they are made out of plastic, way more elastic, and also if something would break, which we don't consider, then they would break first.
Sure. Yeah. I mean, you can certainly test one thing and misinterpret that as being this is the sort of the limit, and then a different part is actually your weakest link, if you will. And I agree that that's certainly something that can come up as well. I think a lot of teams make that mistake where they sort of test one, or they'll do a simulated model of one part and say with perhaps excessive confidence, you know, we will not have a failure here because this part has been modeled or simulated to some extreme amount, and then inevitably something breaks on the course anyway, and all I can do is laugh and say, well, maybe you were looking at the wrong thing, right? Like, you have to probably consider your weakest part, not the one that you would like to test. Anyway, I have one more question, and this is probably just a an oversight on someone's part when prepping the presentation. But if we go to the next slide, slide 6, I think. Yeah, so this is about your drivetrain, but this graph on the lower right, what are we showing here? There are no units or labels on this graph. This is just,
Actually, yes. Actually, thank you that you were asking, because I wanted to explain it, but I thought it would make the presentation too long. So that's why I can explain the graph to you now. So you see the different bars and different colors. You see the blue ones and the red ones. In between, they are also yellow ones. Each of the group, for example, the red segments symbolize like the red until the end of the last yellow ones. They show the 14 gears of our roll of differential gear. But in combination with our Schlumpf transmission at the sprocket of the pilot. You see it on the laser shows it right now. So we have a little gear inside of there called Schlumpf transmission, and it can switch between 2 different modes. One is the speed mode and one is the mountain mode. So the differential gear has 14 gears, and if we drive with the Schlumpf transmission in the first, like in its first gear, you see the red bars until the yellow bars. And if we switch the Schlumpf transition to the mountain mode,
Speed mode.
yes, until the mountain mode, then the gears of the roll-off transmission, they get a bit changed because of the Schlumpf, and that's why the 14 gears add up higher. And if we are realistic, we have actually 21 gears in total if we, see both switches of the Schlumpf gear. So you see the numbers at the bottom. These are the gears.
Okay.
Ja, een beetje holprig.
So okay, so this
Could
is
you follow, or should I answer some more?
sort of. I think so. This is the representation of the different. Is it the different gear combinations between?
Yes.
And then so that's the 20 where you got the 21 different gear sets or combinations, and then the y-axis. Those are representing what again?
These, let me just shortly think about. At first, before I answer this question, I wanted to say, in the middle, the yellow bars are the interfering zone between both of the gears of the Schlumpf. So you see, they are both interfering. So they're almost the same. Sorry, I have to think about. I made this presentation some time ago. What was it? It is the planetarium of the gear in the pedal. So it adds up the toothes that are like needed. Wow. Yes.
Hier slingert ze.
Okay.
I'm sorry, I cannot answer the question to you correctly. I'm
That's all
quite
right.
nervous right now.
That's all right. I was just, like I said, I was just curious because, and I'm not belittling or picking on you, but graphs need labels. Just as a good rule of thumb or a best practice, always include the axis labels, so that in case anyone asks a question. But I don't have any further questions, so I will pass the mic on. Justin, do you have anything for the team?
Justin, we cannot hear you if you're talking.
Actually, he's on hold. He's been called to another meeting.
Oh, my bad. Back to you, Catherine.
All right, thank you. So thank you so much for a good presentation and for a good job answering the questions. Now I'm going to talk to you about something that we talked about last year. But your team members currently in Gateway are listed as invitations sent. So you have sent them the invitation to be a part of the team application, but they haven't accepted it yet. So a couple things that can be done is to make sure the email that they use to set up their first step for their application is the same as the email that you invited them with. And then also they need to check their junk or spam folders to see where those are so that they can accept that invitation and complete their application in Gateway. Because as of right now, you're the only one with a complete application in Gateway who's on the team. There was also someone named Frederick on there, and if he's not a member of the team anymore, you know, that's fine. You don't have to finish it with him, but with the other two, you do need to finish that so that you have all your team members in Gateway.
Okay,
And-
it was weird. I thought we finished it this year.
Well, you're closer this year. Yeah, you're closer this year than last year, but they just need, you finished your part. They just need to accept the invitation and complete the application. So, I mean, you're more than welcome to send it again to them, but again, check the emails to make sure they're the same. You know, that you sent them the email that they used. So that's usually the biggest factor on that. If you get that, could get that done soon, that'd be great. Other than that, I don't have anything for you. Again, thank you so much for your presentation. We are talking about starting office hours up again in January when we're finished with our reviews and such. Do you have any questions for us before we let you go?
Yes, I actually have a question. When are the results sent out?
Those will be early January, right, Chris?
Yes. First week of January.
Okay, great. I think I don't have any other. Oh, I do have another question. I already wrote it to you on email. I think Catherine, you answered. It was about the pit boxes. I know our teams are registered as different teams, like our high school team and our middle school team. But we bring like one set of our tools because we're not able to bring more. And it would be very nice if it would be possible that our pit boxes could stay close to each other so that we don't have to run over the whole pit box area to switch one pliers or whatever. Because, you know, metric tools are different than the tools in America.
No, that makes sense. And we have 10 teams that have both a remote control and a human powered. And our goal is for them to be next to each other. So yes, we're going to do that because that makes the most sense. Even though you're technically two separate teams, you're going to share tools and stuff. So we understand that. Our goal is for those 10 teams definitely to be together. So we will work on that for you all. So you should be good there. So anything else for us?
Maura or Leander, do you have some questions?
No, I don't have any questions. Thank you.
Yeah, I don't have any questions.
Okay.
All right, then you guys have a great evening, and thank you so much, and we will see you soon. Thank you.
See you. It was nice
Bye.
to talk to you.
Bye.
Nice talking to you.